Okay, so I feel like I say that at the beginning of every video. I'm sorry. I'll try to come up with something silly, I guess, to say at the beginning of the video. So, as we said, around 280 is going to be our enthalpy value. Somewhere between 40 and 50 was going to be our temperature. So again, through interpolation, through algebra, we can find this temperature, we can find this enthalpy value. Why? Why do we care? Well, because we want to know the power input. I've already got H1. We were able to look that up because it's saturated vapor. Now I've got H2. I've got V value to find m dot. So the only unknown here now is the power input. Right. So our power input there, you can see they gave us V dot in weird units. Make sure we convert that to kilograms per second. We can find the initial specific volume as we did just a second ago. Now we've got H2 and H1. Now I've got an m dot to go down here. Now it's just plug and check. Now it's just get out an actual number. Okay. Here's where I would ask if you have questions for me. And I wish I could hear you when you're yelling questions at me. I really do. But here we are. Right? So stay healthy, wash your hands, social distancing, all that stuff. I don't like this either, guys, but it's what we got, so I'm trying to make the best of it with you. I really hope these videos are helpful. Let me know down in the comments or something what we can do. Okay? All right. So what's next? Well, a little bit of theory here. So if I've got a reversible process, again, the second law, recall, says that the entropy change is always going to be greater than or equal to an amount of heat transfer per unit temperature. Okay. Now what we're saying is the limit is equal to. Right? The best case scenario is where this is equal to. That's the reversible process where this is equal. And we're saying, look, if it's a reversible process, these expressions or these quantities are equal to each other, and this is just a differential. If you had differential equations, you know we can kind of treat this as a separable equation. I can move this over here and then integrate. So integrate both sides, separate and integrate is what we call that in a differential equations class. Not required knowledge for this course. Hopefully you've had enough calculus, you're comfortable with this idea. Do some algebra, integrate both sides, and then that tells me, well, the total amount of heat transfer. Because the integral of dx is just x. The integral of dq is just q. So if I integrate dq, I just get q. And if I integrate t ds, then I'm just saying, well, just integrate t with respect to s. How does the temperature change with respect to entropy? And that's not something I would expect us to know. But what it does tell us is that if I look at a graph of, say, something like temperature with respect to entropy, and I plotted a process path along here. Well, if I did a Riemann sum, I could I could carve out a little area here, and every little area of this graph represents a little amount of heat transfer that occurs to get from this point to this point. And then the total area underneath this curve represents, again, as we said, Q is equal to the integral of T ds. So if I've got T with respect to S, the area under this curve, the area of this curve represents total heat transfer. Okay? So this is kind of a conceptual quantity that we need to understand. And this shows up here in a little bit when we're going to talk about Gibbs equation. It's a nice concept to have in hand when we get there. Okay? Another useful thing, so it's not uncommon to find diagrams like this in your text. Another useful quantity relationship to talk about is H with respect to entropy, H with respect to S. If I've got a process going from state 1 to state 2, if I plot the enthalpy change, what does the enthalpy change represent? Well, the enthalpy change represents the work that we can get out of, or the work that we, in the case of this compressor, we just saw, right? The work, or the power, is a function of the enthalpy change. And that's what we're saying here is, what are we, Steve, why in the world do we need to even worry about all this stuff? Well, our goal in thermodynamics, a lot of times, is to try to put heat into a device and get work out. or put just the least amount of work in the case of a compressor. So the enthalpy change represents a measure of that work. That's what we want, basically. And what we don't want is we don't want irreversibilities. We want to get as much of this out as we can. Okay, and so delta S basically is a measure of how much is the entropy increasing in order to extract this enthalpy work out. So just kind of something to think about conceptually there. Okay. Now, so the second law is I've taught this course a number of times, and it really, I've just kind of learned over the years, let's just talk about how do you determine delta S, and why is that important? Well, we go back to the first page of notes here. Remember, delta S is really what drives the second law. And we can cause delta S through two mechanisms, through heat or through irreversibilities. And as we saw in the previous problem, we need to be able to quantify this delta S to do some useful things. And that's going to continue. That's going to be kind of the whole goal for us, Chapter 7, is how do I quantify delta S? That's important. Well, we've got some tools for determining delta S. Now, I always say there's three main tools. Right? The first one is table properties. For us in our text, that is okay for water in R134A, not for ideal gases. You do have ideal gas tables, and they were really good if you wanted to find U and H values. You could use the ideal gas tables to find U and H values. I just need the temperature. That doesn't work here for entropy, though. The tables, the ideal gas tables, will give you this S degree or S circle value. That is not S. We will probably talk about this next time. We're not going to get to this today. But just to mention, they don't give you an S value, they give you an S degree value. Water and R134 tables, they will give you an actual entropy value, an actual S value. I just need two other properties, as we saw in the last problem. If I know two other properties, I can find an S value from the water and R134 tables. Not the case for the ideal gas tables. So table properties works good for water and R134. The second way that we can determine delta S, I like to say, is the second law itself. All right, so again, three ways you can determine delta S. First one is table properties, works great if it's water and R134. Second way is the second law itself. Again, remember, delta S, using little s's here, is equal to the integral of del little q over t plus S gen. So what that means is if I can quantify these two terms, I can use the second law to determine delta S. Okay? That's going to come in a number of forms. Do you know something about the heat or the entropy generated? Okay? If it's adiabatic, so there's kind of three main possibilities we could have here. If it's adiabatic, then this integral of del q over t just goes to 0. We saw that in the last problem. Now, if it's not adiabatic, the common thing we will see in this course, again, we're not going to integrate any partial differentials. I'm not expecting you guys to have those calculus tools on board yet. But here's about as tough as it gets, is if you have heat at a constant or average temperature. So if that occurs, if you can assume the temperature is constant, then when I integrate this dq over t, if the temperature is constant, it comes out of the integral. Not a heartbeat there. So I'm just integrating dq in this case. Well, the integral of dq is just q. So if the t is constant, it comes out of the integral, then I'm just integrating dq, and that's just q over t. Right? This is q net in. Right? Again, remember, add the ends, subtract the outs. The third thing that normally pops up here is you need to know something about this entropy generated. In a really weird scenario, you might know the actual amount of entropy generated or the rate at which it's being generated. That's not common. Somebody would have to measure that for you, unless you know it's reversible. If it's reversible, I don't know why I wrote that down. Then you know the entropy generated. It's 0, right? So that's max output, minimum input, things of that nature. Okay? They'll tell you something in the problem statement that tells you it's the best version. That's really what you're looking for, is, am I dealing with the best possible version of this device? If that's the case, then it's the device that doesn't generate entropy. Okay? So two main things we'll do with this guy, this weird integral Q over T. A lot of texts just tell you this is the sum of Q over T, which is really what's going on here. They're saying that add up all the heat in, subtract all the heat out, divided by temperature, each heat transfer divided by its own temperature, and that's all this quantity represents. I understand why this text likes to show you this integral term. It's more generic, but it is a little more confusing. I understand that. This is all we're saying. Add up all the heat, divided by temperature. If there's no heat, awesome, it goes to 0. If there is heat, does it occur at a constant or average temperature? Then just pull the temperature out. The second term, what do I do with it? Well, the main thing is it reversible? If it's not reversible, you're probably trying to find it. Maybe the problem's asking you, is this process possible or impossible? Then they're saying, determine the entropy generated. Okay. Otherwise, either they've given you a value for SGen, or they've told you enough information you can assume that it's negligible, or you're assuming the reversible version. Okay. Those are kind of the things you do there. Right? So yeah, so keywords indicating reversible. The third thing we can use, and this is probably my stopping point, there is an expression we call the Gibbs free energy equation. Maybe you've seen it in the chemistry class. We'll derive a version we'll use here in Thermo and talk about when we can use that. But there is actually an expression that we can use to approximate an entropy change. All right, I'm about 13 minutes or so I'm going to stop there, and I might be able to get the Gibbs equation derived in one video. So I'm going to hear a pop here, and we'll pause there.